Welcome everyone. It's really great to see so many people, and it's really a privilege to see the community of MFEM coming together like this. This is a talk that I gave last time. Since we have a lot of new people, which is great to see. I'll start by brief introduction. Maybe for a lot of you, this is already quite known. But MFEM is a finite element library that we've been developing for quite a few years here at Livermore that is aiming to produce cutting-edge algorithms for powerful high-performance computing applications. And these are some of the highlights of the main features that I think making us successful. We're very flexible in terms of type of grids. So we support both simplex and tensor product grids. We are all about how are the methods and scalability, both in terms on GPU and in MPI, from laptops to the largest supercomputers in the world. We integrated with a lot of other mathematical libraries like Hyper, for example, for solvers, but also things like AMGX, PETSI, Sundials for time integration, and it's all open source. This is the discretization engine for a lot of projects inside Livermore and in the Department of Energy, but we also want to benefit the community. We're part of FastMath, the ECP, XSDK, and of course, the people that are here today, our worldwide community. Now, I mentioned we've been doing this for a long time. This is a brief history. We started the origin of MFEM in a class that we took, some of us at Texas A&M University 22 years ago. So Veselin was there, Stan Tomov, who is now at UTK, was there, I was there. And we used this during internships here in the lab. Then we moved to Livermore from A&M, and we started the BLAST project at Livermore. This is our main application still. And this is what motivated the work for high order non-conforming AMR and the parallel scalability. The repository for MFEM itself started in May of 2010. So we're about 12 years old in its current form. And this was some of the first developers there. Rob Ribben who's in Livermore and leads the Marble team now, was one of the first developers with us. We had a website that went live in 2015. 2017, we moved the full development to GitHub. Prior to that, we developed internally, but now everything we do, all of our work on MFEM is open source and happens in the open on GitHub, and you're all welcome to see it and participate in it. And this is also when the exascale computing project started, the seed project, and we're now, after 6 years of work at the end of this project, it completes this year. That motivated a lot of the work in GPU porting and exascale computing. Okay, so over these years, the code has grown quite a bit. So these are single lines of code, from version 1.0, where we had 22,000, to version 4.5, which we just released this weekend. Veselin will provide more information about the new features in it, which now stands at 365,000 lines of code. And as you can see, the growth has been quite impressive. A lot thanks to all of your efforts, really. And these are the sizes of the different releases and the exact times. At some point, we included internal documentation that we removed at version 4.1. So we're actually now at the same tarball size as version 3.2, but of course, much more lines of code. So the code has grown and the community has also grown. And this is just some of the stats. We have 122 contributors on GitHub. That does not include everybody because, as I said, we had development before GitHub started. Aaron mentioned the MFEM organization on GitHub. There are 541 people in it, and it is really useful to join it. We try to use it as a mail list basically for MFEM because that's how we reach the community. We have about 1,000 stars. We crossed that threshold. A lot of visitors and a lot of commits per day. These are some of our top developers as of or top contributors, I guess, as of October this year. And you will see that there's there's some movement in this if you compare it to next year. So Will and Johan have moved up. In terms of downloads, we get hundreds of downloads per day and tens of thousands of downloads per year from many, many countries. This is the map, more than 100 countries. We really need somebody from Greenland and Mongolia. If you know some finite element developers there, please pitch MFEM to them. This map is kind of empty. There's these 2 empty spots. And for this workshop, actually, I believe we had 220 registered participants of 120 different organizations in 34 countries. Okay, so just very briefly about the last 2 releases. Since the previous workshop, we had version 4.4 coming in March and version 4.5 coming in October. These were a team effort. I always make this video that shows the development and just the number of people touching the code at the same time and working on parallel things. I'll post the slides if you want to watch it. Lots of new features, lots of people contributing, and important things like a lot of GPU developments for this continuous glucose, lower the refined assembly, linear forms, solvers on GPUs, extraction of sub-meshes, HR adaptivity, automatic differentiation for nonlinear elasticity. We have a new mini app called Hook for that, integration with new libraries, enzyme, algorithm, paramonolith, and the list goes on and on. So if you haven't checked them out, please do. As I said, 4.5 just came out this weekend for the workshop, of course. All right. If you're a new user, as Aaron said, your first step should be the examples. These are model problems that you can use to start a bigger application from, and hopefully you have enough pieces there, maybe from several examples to put together for what you need. Now, at the more advanced level, we have the mini apps. We have a lot of electromagnetic mini apps, Volta, Tesla, Maxwell, that demonstrate quite a few different electromagnetic capabilities. And we also have a CFD mini app for incompressible flow called Navier that has been growing in usability and features and applications that use it. And then now we have this Hook mini app that I mentioned that is showing automatic differentiation for nonlinear elasticity. So these are the next level. These are more complicated codes, but with more features, and you can build on them, or you can use them directly for your application with just adjusting boundary conditions and materials and meshes. Okay, of course, ultimately we're impacting large-scale applications in a variety of areas. I mentioned already BLAST, that's ICF, for example, in the lab. We work with engineering in topology optimization and design optimization, for example, for additive manufacturing, but there are a number of codes, Lido and Smith codes. There are some industry applications. We have significant engagement in the fusion and energy sciences program in SciDAC. These are just 2 examples here. There are quite a few applications in kind of, I would say, healthcare industry that use MFEM that has been interesting for us, and many others. And we're always interested in working with applications. Our team enjoys to see the impact of their work. And we enjoy learning about new application areas. So please reach out. Okay, very briefly, I wanted to highlight some of the main advantages that MFEM offers. One is general unstructured adaptive mesh refinement on both simplex and tensor product elements. And we have a number of examples for that. And this a lot of this is also ported on the GPU. And recently we had an improvement of DG plus adaptive mesh refinement on GPU that happened in version 4.4. Another one of the distinguishing characteristics for MFEM is GPU support. We've been doing this for a long time too. We have GPU support in an official release since version 4.0, which is 3 years ago, and we completely reworked the library to do that. These are some recent results from kernels. These are not yet at the library, but this shows you is the work of John Camier, by the way, part of the SEED project. This shows you performance on the SEED benchmark problems of kernels that run across NVIDIA, AMD, and the newer NVIDIA hardware here that can use can utilize this kernel utilizes Git tensor cores. And one of the highlights recently has been to take this curve and push them to the left. This improves the strong scalability essentially by a factor of 10. So we keep working on performance improvements, and we're kind of at the, I think, the forefront of this work on both NVIDIA, AMD, and now also Intel hardware. Okay, this translates to significant benefits to application. This is just a GPU result from the work in BLAST that shows comparison of the 3D throughput hierarchy is better between the old CPU machines and the new GPU machines here in red. And in terms of the speed up in particular phases of the computation, you get 10 to 15 times speed up node to node between the CPU and the new GPU machines that we have in Livermore. This is on the Sierra machine. Okay, the foundation for that has been this finite element operator decomposition. You've seen it, and you'll probably see it more today. It basically allows us to treat the finite element operator as composed of pieces that indicate its action on the global level, on the subdomain level, on element level, and its action at quadrature points. This is partial assembly when we only store and use the data at quadrature points. But what's also interesting is that this allows us to do efficiently derivatives of operators by basically doing them at quadrature points and using the same operator decomposition for automatic differentiation of finite element operators. This is we got a new project to work on that combines MFEM and enzyme, and this is going to be one of the focus for us for the coming years. Okay, so roadmap for the next year, real briefly. Continued the work on GPU support. So particularly the Frontier machine that is very soon going to be available, and the El Capitan machine that's coming at Livermore. They're both AMD machines. We need to port additional integrators and work on continued performance improvements. Address the needs of applications. I mentioned automatic differentiation, in particular for design optimization. That will be a main focus. There's a lot of research in preconditioning, for example, for HDIV, for contact problems. There are things like parallel repartitioning, handling large initial problems. Those are things we're going to continue to work on. Another area is cloud computing, and we're making a significant push in that area too, and you will see some of that in the talk from Julian. MFEM in industry, we're growing in this area, and we'd like to see more engagement in industry and in general approaches for and ideas for long-term sustainability of this project, so we can continue to deliver and support the community. Okay, and then of course we need to work on improving the documentation, adding additional examples of mini apps. I think this is one of the areas where MFEM can significantly improve. We want to improve the code quality. Our plan is to have another release in May. I know last year I was here and I said version 5.0 is coming this year. This will not happen. This year is going to be very busy for us. So version 5.0, where we will have breaking changes and reworking of some of the internals in MFEM and the public interfaces, that will probably happen in FY24. But we can start the work for it, and we're definitely interested in your input and what you'd like to see change if we're allowed to break backward compatibility. Okay, so these are the things that are on our mind, but please let us know what you think. We're doing this meeting because we want to hear from you. Join the Slack and post your thoughts. Post ideas on the issues, or just email us if you prefer. Again, I will put these slides and you can just follow these links. Okay, here are some of the resources. We already mentioned them, the website, the GitHub page. If you're interested in, I didn't talk about the publications, but we're doing a lot of research that ends up in papers. You can read those, and you can communicate on theoretical level too, and you can also just email mfem@llnl.gov.